to the next topic. In this video, we're going to be talking about using power series to solve ODEs. There is a separate short video about a review of power series, so if you're not comfortable with power series, please start with that video. In this video, we're just going to highlight the elements we're going to be using to apply power series in the context of ODEs. Let's look at things. We are just going from second-order linear ODEs with constant coefficients to non-constant coefficients. We're still looking at homogeneous ODEs. So now we're going to look at a situation in which the coefficients in front of y second, y prime, and y is missing again, I'm sorry, are depending on x. We are starting with assuming that p, q, and r, these three functions of x that are in front of y and its derivatives, we're going to start by assuming they're polynomials. If they are polynomials, the first thing we want to do is try to reduce the difficulty of the equations we're looking at. So we're assuming they have no common factor, x minus c, because if they had it, we could just simplify it away. The idea in this context is that we have a specific value of x that we denote x0, and we want to know the solution of the ODE in the neighborhood of x0. And we distinguish two types of points: ordinary points and singular points. We distinguish that by saying that if x0 is not a zero of p of x, then x0 is an ordinary point. Otherwise, it's a singular point. Why is that important? Well, because we usually don't want any coefficient in front of the leading order term. In this case, our equation is second order, so we're referring to y second, the second derivative of y. We usually find it easier to solve it with the coefficient in front of y second is just a 1. So the step is dividing everything by p of x. But if p of x0 is equal to 0, that is a problem in itself. So our first step is assuming that at x0, p of x0 is different than 0. So we can divide everything by p of x0 at x0 and still have something reasonable. If that is not the case, then we have a singular point and we have to do some other approaches. But let's start with the idea that x0 is an ordinary point. Then, as I was saying, around x0, maybe very little around x0, but in a neighborhood of the x0, because capital P of x0 is different than 0, so you can have a little bit of wiggle room before P of x becomes 0. Around x0, as I was saying, we can divide everything by capital P of x. And we have a new equation that is y second plus small p of x y prime plus small q of x y equal to 0. And we're talking about power series. So the step we're taking is to assume that the solution is in the form of a power series. What you want to think about is that we're trying to approximate the Taylor series of y at x0. So we're expecting y to develop as a constant plus something multiplied by x minus x0 plus something else multiplied by x minus x0 squared, and so forth. We compact this infinite sum into this formulation here. This big zigzag thing is a sigma, is a sign that you're summing something, and the indices are underneath and over it. So we're summing from n going to 0, from 0 to infinity, something that we call an x minus x0 at the power of n. Where now an is the new unknown that we want to solve for. So we went from having the problem of finding a function, y, to the problem of finding infinitely many coefficients of an infinitely long Taylor series. It's slightly better because now we have countably many things to look at instead of something that cannot even be counted. So we have done a step in the simplification direction. We still have to solve infinitely many problems. So let's try to do that. Let's start by looking at an example. Y second plus y equal to 0. We don't have initial conditions, so what we're expecting to find is a general solution. We should be able to recognize this equation and know that the solution is sine, the fundamental set of solutions is sine and cosine. But can we formulate it in the form that we have just seen? Well, trivially here, capital P of x is equal to 1, capital Q of x is equal to 0, capital R of x is equal to 1. P of x is always different than 0, so all x are ordinary points. We can assume, because P of x is different than 0, then y of x can be written as an infinite sum. And we set the series around x equal to 0 to make it simpler. So it's a sum from 0 to infinity of an x to the n. We start by assuming that around x0 equal to 0, the series converges. For a little bit. We don't know how much, but we're going to assume that there exists an interval of convergence. If you're uncomfortable with the idea of interval of convergence, I send you back to the introductory video on power series. If the series converges on an interval, on that interval, the derivative of y is equal to the sum of the derivatives of every single term. So we have that y prime on the interval in which y is well defined, because the series converges, y prime is a sum from n going from 1 to infinity of n x to the n minus 1. You might notice that we have changed the bounds from 0 to infinity. Now we have n from 1 to infinity. Why? Well, because the 0th order term, that is just a0 times nothing. The derivative of that with respect to x, it's 0. So we have lost the first order term, the 0th order term. And we do the same trick with the second derivative. So now we write y second equals a sum from n equals to 2 to infinity of an times the derivative of x at the n minus 1, that is n minus 1 times n times x at the power n minus 2. We can rewrite this. We can shift things back to start at 0 again. We do that by saying that we introduce an index that is called m, that is defined as n minus 2. So for the sum that goes from n equals to 2 to infinity, we have a sum that goes from m equal to 0 to infinity. And instead of having a at the index n, now we have a at the index m plus 2. N minus 1 becomes n plus 1. N becomes n plus 1. And x at the power n minus 2 becomes x at the power m. Why do we want to do that? Well, because we usually want to go back to the format in which a power series was first written. So power series are always in the format, well, we strive to get them to the format sum from n equal to 0 to infinity of something 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 multiplied by x at the power n. What you want is that the index on which you're doing the sum is the same as the index at the power of x, and they start at 0, both of them. And that's why we want to give this change of indices from n to m. And now we put them all together. We can change the names of the indices easily. So now we have two sums from n going from 0 to infinity. And the first sum is the second derivative. So it's n plus 2 times n plus 1 times n plus 2 x at the power n, plus a sum going from n equal to 0 to infinity of an times x at the power n equal to 0. Power series can be summed together by just summing the coefficients in front of the x at the power n. So we're taking the sum out and all the coefficients together and then multiply by x to the n. So we have that this is equivalent to say that it's the sum from n equal to 0 to infinity of a block of coefficients times x to the n. And the block of coefficients is an plus a at the index n plus 2 and times n plus 1 times n plus 2. And all of this needs to be equal to 0. There is a theorem that we're revising in the video about introduction of power series that says that if a power series is equal to 0, then all its coefficients are equal to 0. And vice versa, this is the only situation in which the power series is 0 and the only situation in which the coefficients are equal to 0. So, if for our case, what it means is that we have a power series with unknown coefficients, but we know that the power series is equal to 0. So we know that for every single coefficient, that coefficient needs to be equal to 0. That means that we can write that an plus an plus 2 times n plus 1 times n plus 2 is equal to 0 for all n bigger than 0. This is called a recurrence relation. You start at a0 and you're able to recurrently understand the next step. So if you have an, you can compute an plus 2.